Okay, so let me get started. So what I'm going to do today, the title is Self-supervised learning, and you guys know it's depends on the data type, mostly like supervised learnings when you have input and the corresponding or associated output or labeled outputs, we call it as supervised learning. And in the other side is unsupervised learning, which is only thing that we have is input. So we don't have any output, we don't have any labels. And you might heard like semi or semi-supervised learnings and weakly supervised learnings, and there's another type which I'm going to talk about is self-supervised learnings. And I'm going to what the supervised learning is throughout this course, these lectures, but I believe this is going to be extremely useful, and you might see like research opportunities in here in self-supervised learnings. And let's see what it is. And supervised learnings and transfer learnings. Remember, like right after the midterms, we learn pre-trained models, and here one of them is that ImageNet. As pre-trained, a lot of researchers developed, like say, baseline models or good models. We're gonna use that pre-trained models using the transfer learnings to, in that case, the ImageNet case has 1,000 classes. Had a fine-grained image classifications. We use that, and right after that, we kind of believe that this pre-trained model had a good feature extractors, and based on those features, probably we can do later in the downstream networks. We add fully connected layers, and those the layers make it only trainable. So we're gonna do fine tunings. We call it as transfer learnings. Okay. And we use feature representations for the pre-trained models. For the purpose of the transfer learning is that we're gonna use that extracted feature representations for downstream task. So what kind of downstream task? Like we have many, we can use as another classification for specific task, or like object detections and image segmentations and whatever. We call it downstream task. Right? So data, the labelers, we had a lot of like annotations and labels, and we pre-trained the models. Using the pre-trained task, we build up the pre-trained model, right? Right after that, using concept of transfer learnings, we can perform or conduct a lot of downstream tasks. That's kind of typical approach, especially when you have a small data set. Okay. So that's kind of supervised learnings followed by the transfer learnings. Let's think about like what's the pro and cons for related to supervised learnings. And the supervised, whether it's a pre-trained or whatever, it comes with a cost. We need labeled data set, right? So in most of the case, it's a time consuming, and in many cases it's gonna be very expensive. Especially is that the labels, it's kind of requires the domain expertise to get the annotations. It's gonna be very expensive and time consuming, right? I mean, thing is that if you have a good, the prepared training data set, it's like applying a lot of different methods related to supervised learning. That's good. The thing is, the data is very expensive, so that's kind of the hurdle for when it comes to supervised learnings. And for specific task or specialized task, it's going to be downstream task. We need domain expertise. For example, like medical applications, we need like medical doctors to label the medical images. Or, for example, like natural language process and translations, we might need native speakers and language specialists for labeling text in the different languages. I guess you guys can easily imagine the difficulties, things like that. So, like researchers or people are thinking, although supervised learning is good, in order to get prepared for the good label data set, those some have difficulties. So in order to relieve the burden of that labeling issues or annotation issues, like people come up with either semi or semi-supervised or weakly supervised and unsupervised, the unsupervised learnings. And the subtle difference between the semi or weekly, probably you guys can Google it, and there's no, you can easily find the definition of semi or weekly supervised learnings. So those are the topic that it's not topic that I'm going to cover it. I'm going to cover the self-supervised learnings. It's a self-supervised learnings. Okay? And it's, let me see. The definition is supervised using labels. So we're going to use the labels, but that label is generated from data without any manual or weak label sources. It's kind of, so we're going to, this is kind of supervised learnings, because we do have labels. But the thing is, that label is not generated by, generated from the data without any manual resource. That's kind of tricky part. So, self-supervised learning is not part of supervised learning. It's part of unsupervised learning. All right? So actually, we don't need any labels. Probably at this moment you guys know what I'm talking, because it's got confused. But I'm gonna tell you what it is in a minute. The idea is that let me see. The self-supervised task, referred to as the pretext task, there's another term which is pretext task, can be formulated using only unlabeled data set. So as you can see here, we don't need any this step related to labels, because for semi-supervised learnings. Okay. I know this is not a good explanations, but it's gonna be very clear. Let's see. Let me see. So let's see what's the pretext task. So imagine the task that we have is that, suppose we have these two pictures are given, or patches or cropped images. And the question that we have is that after creating 9 patches from one input image, the problem or the task that we have is that we want to build up the classifiers to tell the location information between and middle and the other patches. Okay, so what I mean by this is that we have, suppose we have 9 patches, and the patch in the middle is going to be given. So this will be given. And the network's gonna receive another patch, which is one of them. Let's say 1, 2, 3, 4, 5, maybe 6, 7, 8, 9. I want to build up the classifier whether this image is identified as, tell which classes. You see what I mean? Suppose that's the task. We call it context predictions. So that's the task that we have. And let me ask, so we want to build up the models using the data set or learning based, right? And if you try to solve these problems in the supervised learning matter, you might need, say, you need bunch of pair of data set like this, and this is class probably 1, right? Because it's here in the located in the first. So the idea is that, okay, let me see. A pair of middle patch and other patch is given as the input for the networks. So in this case, you just take any random pictures from the internet, okay, and you crop it. By doing that, you kind of know. So say this is the image in the middle. You can randomly select it either from 1 to 8, from 1 to 8. So you're gonna select it, and by selecting them, you know the labels right after. You know what I'm? So actually, this is not like, you don't need, how do I say? It's kind of supervised learning, but the associated labels is assigned by the developer, by you. So you don't need any extra domain expertise to ask for the labels. Another detailed thing is that, because if that's these, these adjacent it's matched, so the method to avoid trivial solutions probably is gonna make uneven spacing between the patches. That's kind of tricky part. That's one of the example pretext task. Let's see another one. And here, another example pre-task task is, we call it jigsaw puzzle. Again, here I'm going to use the example of 9 patches from the input images. And suppose this one is given to networks. We're going to shuffle it. After the shuffling the patches, we want to make right images. We want to have networks to rearrange it to get this to return to the original positions. Okay, I guess you understand the mission and task trying to attack. So again, we have to build up the classifiers that predict, the permutations, right? Permutations to return to the original positions. How do you do that? What we can do, the only thing that we need is images. And we know the output and shuffle it back and to mix it. And this is going to be the input. Like this. Let me get, say, I guess this is number 1, 2, 3, 4, 5, 6, 7, 8, 9. I guess the way they number is here. And this is the sequence. And actually automatically we can get it from the original image. And we do random shufflings, and this will be the input. And this will be the output. Actually, this is we set up the models in a supervised learning manners, but actually we don't need any labels. You see what I'm trying to do? So another example, let's see. Another pretext task, it will be the image colorizations. So here the question is that given grayscale photograph or images as inputs, we want to do image colorizations. Okay, so again, let me tell you, given a grayscale images, we want to do image colorizations. This is going to be extremely difficult problems. And of course, if this is the inputs, the output is not going to be unique. It's one-to-many problems. So what we can do is that we have to put it in the grayscale images in the input side. In the output side, we have to put it in corresponding the color images. Input and output. So from the data perspective, let's see how we can prepare for that the label data set for image colorization pretext task. Is that again from the internet we can get bunch of or tons of colored images without any difficulties. It's going to be extremely easy. And we do grayscale filterings. We can get rid of the colors, right? We can make it grayscale images, corresponding grayscale images. and these two are paired, and now this is going to be the input, and this will be the output. So, I mean, from the network perspective, this is input and output, but from the data preparation perspective, this will be the inputs. We do grayscale filterings to generate or produce this grayscale. We call it this kind of the self-supervised learning. We train the data generations. I guess you got the idea of what the self-supervised learning trying to tell or say. And see the typical network architectures or structures. And now we do have grayscale inputs, and this is the outputs. And since we're going to deal with the images, probably CNN kind of structure is going to be in the middle as a part of networks. And it's going to predict something. It's going to predict something. And we can define some kind of loss between the predicted and the actual images. That's how we do. I mean, same as supervised learning. We learn or we saw similar concepts when you're talking about kind of super resolutions, remember, and the de-blurring process. We utilize the concept of pretext task or self-supervised learning task. Like here, let's see image super resolutions as another pretext task. So what we can do is, again, let's see how we generate the data for self-supervised learning process in order to conduct image super resolutions. That what if we prepare the training pairs in small and upscaled images? But how we will get original images like this in high resolutions, and we conduct downsamplings to make it smaller. From data preparation perspective, this is the input, and we apply downsampling image processing, one of the techniques, and get it or make it smaller. And this is going to be the input to the networks, and this will be the output to the network. Okay? And since in the middle we have let's see the basic network structures and image in the small size, in the low resolutions, and we need to do some the 2D convolution transpose because we need to do upsamplings, and this is going to predict something, and we do have corresponding high resolution images, which is ground truth, and we have to compute the loss between them, trying to as close as possible. We need to train something in the middle. That's kind of typical idea of self-supervised learning here. And another thing that we can add is that we can add discriminator. You remember the concept that we learned from the GAN? When you're talking about the GAN, we might have generators and the discriminator. trying to as close as possible. Whether this is fake or real. So that's kind of, we call it SR GAN, super resolution GAN. Why? Because we had extra network, which is in the discriminator in this case. But this is what I want to talk about, is that the data generations or data preparations for self-supervised learning. It looks like we do have input and corresponding labeled outputs, but actually it's not. We don't need to spend any extra time or monies to generate labels. Another example is for the pre-text task is image inpaintings. What do you mean by image inpainting? Is that, say, we have this. We do have in the missing part in the middle. We can draw something or painting in. Right? That's the inpainting problems. I want to develop or build up the AI models to do similar task, to do inpainting task. I guess it's going to be, this is extremely difficult problems. But if you apply the idea of self-supervised learnings, then let's see how we do. Again, we have a bunch of different images in the internet. The input, and we're going to do random cropping. Okay. We can do. So we're going to do random missing croppings, whatever. And again, for the network perspective, this is going to be the input, and this will be the corresponding labeled output. Like this. Input with the missing or cropped part inside, and throughout the networks is going to predict or generating something, right? But we know the ground truth because this guy is coming from the original image. And we can compute the loss. Of course, trying to make it as close as possible. Another extra thing that we can do, again, the same concept is we can add a discriminator, whether these two are real or fake. That's how we do inpaintings, using the concept of self-supervised learning. So I guess I went through a lot of different examples related to pre-text task. Let's see what was that. The first one was the context predictions, and the second was the jigsaw puzzles and image colorizations and super resolutions and deep loadings as well, and image inpainting problems. And I guess you got some idea of how we do the self-supervised learnings. And the reason that I wanted to include this topic in this course is that whenever you do your own research, and say I wanna do problem solving with the data-driven approaches, and the first issue that you guys might see is that you have the data shortage issues. Or say I do have a bunch of data set, but I don't have any labeled data. So in that case, please think about this kind of the approach, which is pretext task or self-supervised learnings. How can you add or get labeled data set without spending too much money or time? And let's talk about benefit of self-supervised learnings. And like supervised pre-trainings, we can learn general purpose feature representations for downstream tasks. We can reduce the expense of hand labeling the large data set. Okay. And this is going to be the most important slide in related to self-supervised learning. Is that let's see the pipeline of self-supervised learnings. And here, the downstream task is going to be like you can do anything, but say this is classification problems. Suppose this is one of the classification problems that you have. And the idea is that, say we do have bunch of data set, but say it's unlabeled. The only thing that you can do, or one of the options that you can do pretext task, and you will get kind of pre-trained models. Okay, but this pretext task is of course it's going to be different from your downstream task or the task that you want to have, right? But the good thing is that, or the assumption that we have is that these networks mostly relate to feature expressions or good feature representations, and we can apply the idea of transfer learnings, and we're going to fix these. We're gonna fix these, and we're gonna have like the downstream layers, which is mostly related to classification task. So these weight and bias, we can make them fixed, and these are to make it trainable. But in this case, instead of training the entire networks, and this is the only thing that we need to train. So since we have small parameters that we need to estimate it, we don't need the big data set. We might achieve the similar performance using small data set. That's the idea of, or the pipeline of self-supervised learnings. So all the examples that I explained so far is related to the top part, related to pretext task. Once we have models, we build up the models using the pretext task. We can use that the part of models apply the transfer learnings. For specific task, it's going to be the downstream task and the task that I want to achieve. Why is that possible? Because I guess this one was the slide that I showed you when you do the deep artificial neural net. And if you have a bunch of hidden layers, and this part is, we can consider it as a feature learning process. Right? So the assumption or the belief that we have is that the feature learning process, we think, although we have different tasks, since the input is the images or the same type of data set, we believe that the feature extraction is going to be pretty much similar. Pretty much the similar. So let's see one by one. Within pretext task, deep neural net learns visual features the input unlabeled data set. Right? The learned parameters, we can make them fixed. And these are pre-trained networks going to serve as a part of pre-trained models for downstream tasks. The pre-trained models is going to be transferred to the downstream task and do fine-tunings, like transfer learning. Like transfer learnings. Okay. These two are the same, but only it's different, the figures. Pre-training data with data and pre-text task, we do models and predictors, and we transfer the knowledge that we learn here for the task of downstream task, all right? And just the only thing is that we do fine-tunings, like transfer learnings, using task-specific small data set that we have. And here is going to be a bunch of, but it's unlabeled. But we can make it like a supervised learning process because we're going to do pre-text task. We can make labels. So let me see. That's it. In this data set, we're gonna do the class again. I'm going to show you the one of the examples that I prefer for the downstream task. And suppose the task that we have is an MNIST data set, and we want to do classifications from like handwritten digits from 0 to 9. We have 10 classes. We did that in using the ANN or CNN or whatever. We know that this is not a difficult task, but somehow we assume that that's extremely difficult. At the same time, suppose we don't have any, like we do have small data set with labeled, corresponding labeled. In that case, I want to apply the concept of self-supervised learning. Like 5. And if you have, this is labels, right? We know that. But suppose we have tons of MNIST data set without labels. And what kind of pre-text task that you guys can think of? Anything. So here, another pre-text task is rotations. So this is the only thing that we have. No labels. We don't know what it is. This is the only image that I have. Okay. And we have to think about some kind of related pre-text task. There are many, but one of them here is that here. So this is the image that you have. And I'm gonna rotate it. So like with a 0 degree, 90 and 180 and 270. So again, here, this is the input. I don't know whether this is 5 or not. I don't know. Suppose I have no idea. And one thing that we can do is that I can rotate it and make it as a classification problem. the output is that we have 4 neurons, like 0 degrees and 90 degrees. And I'm gonna have image and I'm gonna randomly rotate it. And since I rotate, I know the corresponding label. You see what I'm trying to do? We don't need whether this is handwritten, this corresponding 5 or not. We don't need. And here, what I explain is I want to do self-supervised learnings. But what's the corresponding pre-text task? Is that I'm gonna rotate it the entire input images. I have 4 different options. And since I'm gonna rotate it like 180s, I know corresponding label. I mean, this has nothing to do with like whether this is 5 or 6 or 9. We don't need any information for output. And we can make it with using this kind of trick, we can treat it as a supervised learnings. Okay. But the hypothesis behind is that this model, this model recognize the correct rotation of the object. It's only if it has the visual common sense of what the object should look like. So we're hoping that by doing this rotation pre-task, I mean, here we have to extract some of the good features, right, in the MNIST data images to see whether this is 0 or 90 or 108 rotations. So we believe that even though this is kind of pre-task problems or rotation problems, we're hoping that this kind of the model is we hoping that it's trying to extract good feature representation. So just copy and pasted it. Remember, the original problem is classification problems. And we're hoping that these feature extractions, we copied it. Only thing is that we just do fine tunings related to like classifiers or predictors and this part. Right? We can do with a small data set, because we have smaller parameters to estimate it. Here we have to, instead of estimating the entire parameters, this is the only part. This one, we got it from pre-trained model. This is you don't have to do it. This is one of the ideas, related to pre-task tasks, but I think the idea is kind of brilliant. It's brilliant. Here, the only thing that we need has just input images. Why? Because I'm going to rotate it. That means I know the corresponding label. So using that labels, we can do kind of supervised learnings. We call it self-supervised learnings. Using that, we want to get the pre-trained models. Then we can apply the idea of transfer learnings, trying to attack the downstream task. In this case, it's going to be the like classification for handwritten digit. I'm gonna show you. We call it this is it's a rotation, so it's I don't know how it's ROTNet or ROTNet, whatever. So I'm gonna show you how to implement it for self-supervised learning using the MNIST dataset. So let's see. We need to generate rotated image and their labels to train the model for pre-text task. And here I'm with this example, like we do rotate it 90 degrees. And this is the data generation part for pre-text task. And we use one-hot encodings to label it. And we can build up the CNN models. We can build up the CNN models, like comb max pullings and comb max pullings, and later we flattened. We do these classification problems. I mean, for pre-text task, here we do have only 4 neurons because it's a rotation classification problem. It's different from the 10-digit classifications. And these are number of total parameters, and all of them we need to train. Okay. We do have a lot of MNIST data set in this case. The only thing is we assume that we do not have labels, but we generate the labels in terms of rotations. Okay, we build up the CNN models now. So we build up this model. Now I want to do transferring that knowledge that we learned, the model learned from pre-text task. And for downstream task, now it's another classification problems. Let me see. We freeze the train parameters, right? We have to fix it. We have to fix. So we make it this pretext transfer false. We're freezing the train parameters, and then we transfer them to the downstream task. For downstream task, which is MNIST image classification problems, here these are fixed. Only thing we add, we had the dense layers. We add another hidden layers right after that. And remember here is we have 10 neurons because we do have MNIST data image classification in this case. And here the total number of parameters is this amount. And most of them we try to make them untrainable. So only we do have small part of trainable parameters, which is like dense layers at the end. So we do have only like 2,000, like with 3,000, around the 3,000 weights and bias, which is small number of trainable parameters that we need. And most of them are non-trainable. That's the way that we set up. We're hoping that this part is kind of, we learn a lot of good feature extractions from pre-text task. That's what we are what we are hoping to. Okay, small number of. Okay. So here, two convolution layers are transferred from the model from the pretext task. So all of them are, all the related to the two convolutions, we make them as non-trainable parameters. And we add single fully connected layers, trainable only. So that's kind of the work that we did, the self-supervised learnings. And in order to make comparison, let's do supervised learnings as well, because we have to make some kind of comparison. And we learn a lot of things related to MNIST image classification problems. And suppose we have, convolutions, max planes, and convolution max planes, and flattening and dense layers. That's kind of typical classification problems. And we make all of them. We have, these are the total number of trainable parameters. We just did supervised learnings to make comparison with the self-supervised learnings. That's kind of what we typically did. And this is, let me see. We evaluated the accuracy. So it's a supervised learnings, and this is kind of accuracy that we have. Like 83%. Why is that? Because remember, this is, if you have, suppose we have enough data set, this is going to be like almost 100%, but we kind of assume that we do have small label data set. So that is kind of the performance that we have. And here, this one is that we got from self-supervised learnings, and like accuracy is like around 86%. Here, like 3% difference is not that big, but the numbers, and you don't have to worry about it. Here, the only thing is that I want to introduce the concept and demos related to self-supervised learnings using because the MNIST data is most familiar with. So let me summarize things that in real research problems, most likely you're going to have small data set or small label data set. In that case, in most of the time, you're going to fail if you apply to supervised learning method because you don't have many data set, right? In that case, first thing is that you have to think about how can you increase the number of data set, or how you gather more data set, or you can apply the data augmentations, whatever. And the smarter way is here, self-supervised learning. This is much smarter. It would be good if you have come up with related pretext task, then apply transfer learning ideas to increase your performance over accuracy of your model for downstream task, which is your specific problems or task. Okay. So these are all the contents that I have related to self-supervised learning. Again, I believe that the idea of self-supervised is really important, especially when you have small label data set, and it's going to be very useful even for your own research. You apply the idea of self-supervised learnings. And we have homework assignment, and I think this is on Thursday. So okay, so probably I can stop here. So probably.